So, the numbering is like this. Module 2 in chapter 1 will be designated as module 1.2, 1.3 like that. If it is chapter 2, it will be module 2.1, 2.2 like that. The first number is the chapter and the second number is the module after the point. We introduced the concept of EMI and EMC in module 1. In this module, we will go through common sources of transients, common EMC units, and also the concept of common mode as well as differential mode currents and voltages. Now, anything that can produce electromagnetic energy is a source, a noise. It can be any kind of transmitters producing electromagnetic energy. It can be mobile phones or it can be radio transmitters, radar or anything. And any switching events can potentially, if you just switch on the lights, it can produce the sparking at the switch can produce noise, both conducted as well as radiated with certain frequencies content in it. The lightning, the natural phenomena like lightning, that is a severe source of EMI problems. Then we have electrostatic discharge from rubbing two materials together or from human body when you pick up some components or something, there can be discharge happening between the body and that object. So, that also is a source of EMC and can potentially harmful to electronics. Now, let us look at lightning. What is shown here is one small portion of a lightning current waveform. It is called a lightning return stroke. We will see more details of lightning when we discuss on lightning protection. So, here this is the time. So, the time base is in microseconds. So, the total time is 50 microseconds here. The whole lightning flash may last up to 1 second with several events in it. So, this current, this peak current for this particular impulse, it is in terms of kiloampere. So, 16 or 18 kiloampere over here. So, this is an example of return stroke wave shape. So, the 10 to 90% rise time let me take the pointer, yes. So, the 10 to 90% rise time of the wave front is 0.36 microsecond. So, the currents up to 100,000 ampere and rising to the peak in a fraction of microsecond can be produced by lightning return strokes, and the potentials can be of the order of millions of volt, and this produce very large electric and magnetic fields. Very close to the lightning, you can have fields of the order of 100 kilovolts per meter, that is extremely high electric fields. So, more details we can see in the lightning protection. Now, switching transients. Switching transients are very common, a common day occurrence whenever you switch any device or lights. So, typically what happens is that suppose you have a source, here a battery is shown and a switch, a mechanical switch that is closed and open, and your load may be in the form of resistance and inductance. Inductance is a storing element, it can store electromagnetic energy, And you can have parasitic capacitance here, because if you have two metal pieces across the switch contacts, you can have a capacitance across it. It may be in picofarads, but still there is a capacitance. So, this inductance and capacitance together, inductance of the load and parasitic capacitance together can form a resonating circuit. So, and this coupled with the breaking and closing of the switch can create noise. Say for example, across the switch you have a potential difference between these two, and when the switch is opened, this potential difference will create a arc sometimes. So, you can have switching with arcing and without arcing, and with arcing it will have more severe noise issue, EMI issue. For example, the sketch of a voltage without restrikes. Restrikes are called this arcing at switch contacts, because voltage across this may be time varying because of this resonance phenomena over here, and without arcing you can have a damped sinusoidal waveform across the switch. And but with arcing you can have several restrikes, and finally it comes to a steady state. Sketch of voltage V with restrike as switch contacts, and this time is in milliseconds per division. So, you can see that there are high frequency content in this arcing. So, depending upon the design of your circuit and the switch, you can produce devices that produce lot of noise or less noise. Electrostatic discharge. Electrostatic discharge occurs when a charged body is brought near another conducting body, and the static charges are generated whenever two different types of materials come into contact and are then separated. So, this is called triboelectric effect. The common situations where triboelectric charging occurs are when people are walking on a insulating mat or a carpet, clothes rubbing against the skin, plastic or paper moving on a roller in industrial processes, handling of electronic components. Now, ESD is a big problem in paper industry and plastic industry whenever you have situations of material passing over rollers, because it can produce micro dimensional pinholes into the materials. So, they have to control electrostatic discharge at any cost. While handling electronics, you use straps on the wrist, then grounded to reduce the danger of your body getting charged and damaging the components. So, potential difference between a charged person and ground could be a few kilovolts and may produce discharge with rise time of a few nanosecond. So, few nanosecond means that you are talking of frequencies of the order of several hundreds of megahertz and close to gigahertz. Then within electronic components, ESD also create intense electric and magnetic field in its close vicinity. So, it can couple to other adjacent printed circuit tracks and create problems. So, what is shown here are some typical ESD waveforms. So, this is an example of a current waveform, time in nanosecond and current in amperes. So, this typically represent a human body type of ESD, the interaction between human body and some metallic devices. And this shows the magnetic flux from that type of currents, and this shows the electric field strength measured at this is around a few centimeters away from the discharges. Now, what could be the possible spectra that can cause EMI? In fact, it can be any known spectra of radio frequencies and low frequency waves. So, this is this graph is taken from the International Electrotechnical Commission standard 61000. The details of the standard is given here. Electromagnetic compatibility part 213 while defining the high power electromagnetic environment radiated and conducted. So, this is a website, but even though this particular standard is talking of high power electromagnetic interference, the spectrum here covers the complete frequency spectrum of radio waves, say, and this spectral density. So, 10 kilohertz. So, we are in the power line harmonics, 50 hertz harmonics are somewhere here. Then switching transients may be somewhere over here, and lightning, it has got very high energy at low frequencies, then it is over here. High power electromagnetic pulse from nuclear explosions and all, it has got much wider bandwidth up to 300-400 megahertz. Then narrow band, high power microwaves, high intensity radiated frequencies, etc., that they come here in small narrow bands or very wide band single narrow pulses. It can come over here, and cell phones are operating in this kind of range where they can be susceptible for this type of frequencies. So, basically as far as noise is concerned, the whole spectrum starting from sub 50 hertz even DC to several gigahertz are possible candidate for EMI problems. Now, some examples from IEC standards are taken to show the waveforms of not very common sources of EMI issues, but if it happens, that becomes severe because it can affect the whole cities or whole countries. For example, high altitude nuclear electromagnetic pulse. Many of the critical systems in several countries are designed to withstand high altitude nuclear electromagnetic pulse, critical command and control systems of military and civilian systems in some cases. For example, the E1 component of the HEMP waveform has here time scale is nanosecond, and here it is in kilovolts per meter. So, those if it is defined that it should withstand HEMP, then this is the type of waveform that are considered in civilian systems. And the E2 component or E3 component of HEMP waveform that is shown here. Here the time is in seconds, so 10 seconds, 100 seconds. So, high altitude nuclear EMP E3 component is it has got a lot of energy, but these amplitudes are much smaller, but it can produce problems with very long transmission lines, very long pipelines, etc. So, this is a kind of a composite waveform showing E1 component, E2 component and E3 component, and this is in time scale and this is in the frequency spectra. So, this is the kind of source that one has to design the critical system against. So, we also have geometrically induced currents. Now, you have solar flares, the kind of it's part of the solar weather system. When solar flares comes, charged particles are getting ejected into Earth's magnetosphere, and this causes disturbance in the Earth magnetic field, and it can last several days. So, this magnetic field disturbances are very small, only 2 microtesla in peak. It is quite small, which can have a rise time of about a minute and fall time up to several minutes. So, in terms of waveforms, it is more comparable with the E3 component of the nuclear EMP. But this induces very slowly varying DC voltages of less than 1 hertz in large distributed metallic system of the order of 10 kV per kilometer. So, this can even though this may look very small, this can drive power transformers into saturation, and power transformers in the power network are extremely rare pieces, specialized components, and you do not have many spare devices around the world. Huge power transformers of several mega MVA in rating. So, when a couple of them are disturbed, it can create blackouts over large portions of the land. So, solar flares and geometrically induced currents are quite a threat, and this has happened in northern Canada, and it can happen depending upon the space weather. So, it is more of a threat in the higher latitudes than towards the tropics. Now, we will go through some of the concepts used in EMC. So, we have finished with some of the description of the sources. So, one is the concept of electrical dimensions. So, we have a physical dimension, say 1 meter, how much it is we know, 10 meter, we have an idea in the mind. But when we in electrical engineering, whenever we have alternating currents, or in electromagnetics, spatial distances has some meaning, but more meaning is attached to electrical distances. So, that is what we will define here. For example, for a plain electromagnetic wave in a lossless media, we have the wavelength given by the speed divided by the frequency. So, speed of the wave in the media and frequency in hertz. So, in air, V is the speed of light, 3 into 10 to the power of 8 meters per second. So, frequency is number of cycles per second. So, you can see that wavelength is given in meters. Now, let us see what does it mean by 1 meter distance between system A and system B. Let us say there is a cable in between system A and B. So, we say that this cable is 1 meter. So, what does it mean? If you have a signal from here to here, and that signal frequency, center frequency is 3 megahertz, it means it is 0.01 wavelength only, because at 300 megahertz the wavelength is 1 meter. So, that is the speed 3 into 10 to the power of 8 divided by frequency 300 megahertz, that will give you 1 meter. So, this is one wavelength at 300 megahertz, but if it is 1/100th of the frequency at 3 megahertz, this is only 0.01 wavelength only, because the wavelength at 3 megahertz is 300 meters. Sorry, 1000 meters, 100 meters. So, it is 1/100th of the meter. And say for example, wavelength at 3 gigahertz, we have 3 into 10 to the power of 8 divided by 3 into 10 raised to 9. So, it is 0.1 meter only. So, 1 meter will become 10 times wavelength. Therefore, 1 meter of physical length is 10 wavelengths at 3 gigahertz, but only 0.01 times the wavelength at 3 megahertz. So, 1 meter is electrically long at 3 gigahertz. So, we will introduce the concept of electrically long and electrically short. Often we will use this term. So, then if we say that 1 meter is electrically long, say it will be electrically long if it is at 3 gigahertz, because it means 10 times wavelength at 3 gigahertz. So, it is several wavelength. So, you have several wavelengths at 3 gigahertz, whereas at 3 megahertz, it is covering only portion of a wavelength. It goes like that. So, it will be electrically short. The same distance, same cable will be electrically short or electrically small at 3 megahertz and electrically large at 3 gigahertz. So, these concepts we will be using very often. Now, in dielectric media, the speed of electromagnetic fields are different, electromagnetic waves are different. So, there while discussing the fundamentals of electromagnetics, we will review this. We have magnetic permeability of air or vacuum given by 4 pi into 10 to the power of minus 7 Henry per meter. Electric permittivity of air or vacuum is given by 8.85 into 10 to the power of minus 12 farads per meter. So, V is 1 by square root of mu epsilon. Mu epsilon has got two terms, mu 0 times mu r, and epsilon is mu 0 times mu r. So, if we separate it out, we can write it as c by square root of, because this part is the speed of light c, 1 by square root of mu 0 epsilon 0 is c. So, c by this relative permittivity and permeability. For example, in paper mu r is 3, so sorry, mu r is 1 and epsilon r is 3. So, the velocity is 1 by square root of 3 times 1 by square root of 3 of the speed of light. So, 1 meter of physical length in the medium of paper is 17.32 wavelength in paper. So, whereas it was 10 in air. So, depending upon the medium, again electrical dimensions can change. So, a concept that we frequently use in EMC studies is decibel. It comes from sound engineering to measure the amplification of the sound, but then later it was used in other areas including electrical engineering and electromagnetics. So, decibel is a logarithmic quantity used in sound and radio engineering. and it is denoted by D and capital B, dB, small d and capital B. So, it is originally defined as ratio of two powers expressed as 10 log to the base 10 P1 and P2. P1 and P2 are two powers. So, one may be from the signal source and one may be after amplification. So, you can see what is the gain. So, gain is P1 by P2, it's some ratio of powers you can define. So, 10 times log to the base 10. Now, the reason for defining decibels is that often in EMC studies or electromagnetics, you deal with magnitudes that are several orders, 10 to the power of 8, 10 to the power of 10, like that. So, you can't express it on linear scale, it is very difficult in a graph, whereas you can say 10 to the power of 10. If you want to express it in equal divisions, you need to have so many divisions, it is very difficult. But if you are expressing it logarithmically in 10 divisions, you can express 10 to the power of 1, 10 to the power of 2, 10 to the power of 3, like that. Then you multiply by 10 arbitrarily, it is defined like that. So, R ratio dB is 10 log P1 by P2. So, it is a unitless number because power is watt is divided by watt. So, it is unitless, but at the same time you want to know what are the reference units being used. It makes a difference whether it is watt or milliwatt in the final number. So, to denote that, you will add the unit beside dB, even though dB is a unitless number. Now, later the concept of dB is extended to voltages and currents, electric fields and magnetic fields, etc. Then there you define it as 20 log ratio of voltages. The reason for that is that, say for example, power is given by voltage squared by R, or where R is the resistance, or I squared R, I is the current. So, here you can see V squared and here you can see I squared. Then this 2 is taken over here to become 20 log V1 by V2 or 20 log I1 by I2. So, being a ratio, decibel is unitless, but we refer to it as dB microvolt, dB referred to a microvolt, or dB watt, dB referred to a watt, or dBm, dB referred to milliwatt or millivolt and things like that. And if it is voltage or current, we define it as 20 log the ratio. If it is power, 10 log the ratio. Now, some examples are given here. Say 10 volt is equivalent to 20 dB volt. How do we get that? 20 log to the base 10, 10 volts, and your reference is 1 volt. Then log 10 is 1, so you get 20 dB volt. Say you can express instead of volt in terms of millivolt or microvolt. So, if you take 1 volt, which is equivalent to 10 to the power of 6 microvolt, that will be 120 dB microvolt. Say 20 log 1 volt divided by 1 microvolt equal to 20 log 10 to the power of 6 is equal to 120 dB microvolt. So, common references in EMC studies for electric field and magnetic field are dB microvolts per meter and dB microampere per meter respectively. That also comes from the same relationship. It will be 20 log ratio of electric fields or 20 log ratio of magnetic fields. So, from that this can come. Now, we can convert from dB to the referring units, to the opposite. For example, 44 dB microampere per meter. Suppose we want to convert it into microamperes per meter or amperes per meter, let us say. So, how do we do that? So, from this presence of microampere per meter, we know that the base is microampere per meter for the magnetic field intensity. So, we do the reverse of this. So, it is 10 to the power of 44 dB microampere per meter. Since it is magnetic field, we know that it is definition is 20 log. So, that divided by 20, 10 to the power of that will give you 158.49 microampere per meter. So, this you can further convert it into say 0.15849 milliampere per meter, or 158.49 10 to the power minus 6 amperes per meter, like that you can write. So, the process is divide the quantity by 20 if it is voltage, current or fields, or by 10 if it is power, then raise 10 to that power. So, this is the procedure for converting from dB to the referring units. Now, another concept we will see very often and which has got a great significance in EMC is differential mode signals. Differential mode means that difference. What is that? And also the common mode signals. Say in the first one picture over here, you have a source and you have a load. So, the source is producing some, it can be alternating current or DC. So, this shows one instant of time. So, you have a current flow like this and a return current of equal magnitude like this. So, this current and this current are the same, but opposite in direction. So, this is called a differential mode. So, normal signals are all differential mode signals, and there can be some noise EMI also circulating in the differential mode, say for example, some of the switching noise or some other electronic noise. So, this is a ground plane. But it could also happen that you have some fields, electromagnetic fields coming from some other direction, and it is falling on this circuit over here. Then you create a potential difference between your lines and the ground because of the interaction of the electric and magnetic fields, and that will drive some net currents. You can have parasitic elements, parasitic capacitance here or some other connections, and it can drive some currents through these lines, through the ground and back into this. So, it is as if you have some source here, this is a fictitious source here. I mean, this action of the electric and magnetic fields can be modeled as a fictitious source that is driving a current, common mode current through this and back through this. So, this is I subscript Cm, and this will be the total common mode currents falling back. So, if you just take this part of the circuit alone, what you experience is just currents in the same direction and same magnitude. So, this is called the common mode currents. So, this basic decomposition can be done. Most of the lines will have both differential mode and common mode currents, even though common mode currents can be quite small. For example, a power lines normally carry differential mode voltages currents. When subjected to distant lightning, electromagnetic fields or voltages are induced in all the lines with respect to the ground. This in turn drives currents in the same direction along the line via the returning ground. So, this is one example of common mode currents in power lines. And you can have both common mode currents and differential mode currents at the same time. So, why common mode and differential mode currents are important in terms of radiation, radiated disturbance? You can see it over here. Say for example, if there are currents in two parallel wires I1 and I2, then I1 is I common mode times I differential mode, and I2 will be, since differential mode direction is changing, I common mode minus I differential mode. Then the current along the ground is I1 plus I2 or 2 times ICM, or you can define differential mode currents as sum of these currents divided by 2. Because differential mode currents are cancelling each other, and differential mode currents are difference in these two currents I1 and I2 divided by 2, because common mode currents are cancelling each other then. So, this since they are in the same direction, it can produce quite large fields even with a small currents at a distance, whereas if it is a differential mode, these two currents are opposing each other, so it will not produce as much fields far from it. Now, this type of common mode currents can be produced in any 3 conductor system when subjected to external fields. So, they are very common. For example, 2 wires above a ground plane, a 3 wire conductor system, it can be 2 wire shielded cable or a coupled strip or a coupled